I'd like to welcome everyone to the virtual seminar on climate economics. I'm Glenn Rudebush, a senior fellow at the Brookings Institution at the CEPR and at the Stern School of Business at New York University. The Center for Economic Policy Research, the CEPR, especially through its Climate Change and Environment program, has provided key support for this seminar series. And my seminar organizers include Mar Regwant from Northwestern and director of that CEPR Climate Change and Environment Program, Fran Moore at UC Davis, and Lynn Barrage at ETH Zurich. The virtual seminar on climate economics covers a wide range of topics on the economics of climate change, drawing on macroeconomics, microeconomics, finance, econometrics, international, and environmental and energy economics. Our speaker today is Ghassane Benmir. Ghassane is an assistant professor at IE University in Madrid, and his research explores the linkages between macroeconomic theory and heterogeneity, asset pricing theory, climate change, and the distributional impacts of both environmental externalities and policy. As we shall see, he uses theoretical and numerical modeling as well as empirical approaches. Today, Ghassane will talk about green asset pricing. There'll be 50 minutes for his presentation, followed by 25 minutes for questions and discussion. To ask a question, type it into the Q&A and raise your hand. During the presentation, we will cover clarifying questions, but the bulk of the questions should come after the presentation. We are recording this seminar for posting online, but we are not recording the Q&A session. Ghassane, thank you very much for joining us, and the virtual floor is yours.
Hello, thank you very much for having me and for the very nice introduction. I very much appreciate. Very happy to be here with you. I'll be presenting one of my papers, Green Asset Pricing, which is joint work with Gauthier Vermondel, who's at École Polytechnique in Paris, and Yvon Jacquard, who was at the ECB. And sadly, Yvon passed away a few months ago. And in his honor, this will be actually the first time I'm presenting the paper like to a large audience since his passing. So I hope that I'm going to do a decent job, especially that I know how much he held this paper really dear and close to his heart. So from wherever he is, I hope that I'm going to make him, to some extent, I don't want to say proud, but at least don't disappoint him too much today. So shout out to him. And I think I left this also just to never forget that actually he's one of the central parts to the paper. He used to be at the ECB, so this actually is pretty much for him. So he never really left the ECB because the moment he passed away, he was still there. So it represents our views and not those of the institutions, such as the ECB, for instance. But what is really the paper about? In fact, it started as a long project since I started my PhD, knowing both Gauthier and Yvon, and we tried to understand, and we took it from that point in time, is that what would be the role of finance in trying to understand the implication for climate policies, and especially the carbon pricing. So what we do here is we're trying to really use some empirical grounding of the stochastic discount factor, which I will explain that is one of the most important elements of carbon pricing in order to determine what would be the optimal carbon price. So this is really the main question at heart of the paper. Now, a lot of countries has pledged for a net zero policy. Now, again, like we'll take this as a status quo, right? Like the political framework is shifting around quite substantially all around, but at least here in Europe, I think, and pretty much all different parts around the world, it's still one of the pledges that are really important. So going to a net zero by 2050 would require the whole economy to try to think about what would be the correct kind of carbon price that we should set, as emissions have to decline to basically some net zero by the timeline that we have in mind. So setting the right carbon price will be key. I have even different type of work that tries to look at what would be the heterogeneous impact of this sort of carbon pricing and climate policies, and how would they impact people like from different income baskets or brackets differently. So setting it right is really, really important for a just and a net transition toward like the goal of like net zero by 2050. So the social cost of carbon has these elements, and when I say the social cost of carbon is essentially just what is the optimal carbon price that we need to set in the economy, features, in my view, 4 different type of elements that comes at play and interact between each other in order for us to basically be coming up with the correct pricing. Those four elements can be summarized as the discount factor, the SDF in this specific case, the stochastic discount factor. So it includes some element of uncertainty, that's the expectation in front of the brackets. But it's a function of this stochastic discount factor, some long-run growth, some climate dynamics, and climate damages. Those are the four probably main elements that would interact for us to be able to speak about this type of fiscal policies. And in a big nutshell, this discount factor, which is the one that I will be focusing on in this context of this paper that we have, is one of the central elements that has brought a lot of debates. And I think I summarize it here as Nordhaus versus Stern, where essentially an approach by William Nordhaus tells us that we can use some sort of market factors or market interest rates for us to think about the stochastic discount factor, while Nick Stern thinks about some discounting that could be more normative as such that we can capture long-run projects that aim to reduce climate change and privilege the future generations over the current generations. So this debate has kind of fueled a lot which type of discount rate should we use, as that would have a substantial impact of the carbon price today. And this is to which, or at least the literature over which we're trying to answer, or at least have some work that speaks to. But the other three elements in terms of climate dynamics, climate damages, and long-run risks are also subject to a long debate. And I think I'm kind of like hinting in the couple of bullet points here on some of the key papers, or at least the recent papers that have brought some attentions to that. I think in climate dynamics, one could think about like the impacts of different type of calibrations and also specifications of the climate dynamics. I think the latest work by Follini and all tries to revisit the Nordhaus DICE model and shows that the implications of having different type of calibration can be really important. The climate damages, I think the latest work of Bilal and Kenzig also kind of revisits these climate damages that has been shown in their work to have substantially higher level on damages, and thus can propagate and get us a carbon price that is substantially higher than when what we used to basically see in the standard variations of the DICE models. Speaks also to the earlier work of Martin Weitzman with respect to tipping points and uncertainty as well. And there is an element of the long-run risk, especially from a growth perspective. And I think it relates well to a lot of the work that has been done in finance from Benson and Yaron up until their latest work in 2017 that tries to include it in the climate sphere. Now, the paper really looks at the discount factor, and this is the component that I will be the most interested in. But again, I don't want to put everything out of the table. Those are other three elements that are also really important in setting up the right carbon price. But in the context, we're not going to be specifically going into trying to address those three others. So again, the social cost of carbon is just a financial asset. It's the main component of it, or one of the main components are the stochastic discount factor. So I'd score determining the social cost of carbon is fundamentally an asset pricing problem. And I hope that Glenn does not disagree with me on that, given the long work he has on this. So central to this social cost of carbon calculation is, therefore, if I say it's the stochastic discount factor, will be the utility function that we will be using. So the stochastic discount factor will be just a derivation of the utility function, and as such, having an understanding of which type of modeling macrofinance framework that we will impose on the utility function will have substantial impact on what stochastic discount factor we will have, and therefore will propagate to the carbon pricing. And this can have a lot of potential implications, both in the macroeconomy at large, but also in the financial markets. And I think a lot of the speeches, whether it's about the ECB president, Christine Lagarde, or other executive members, Isabel Schnabel or others, speak and stress a lot on the implications of potentially climate change on financial assets. And as such, fiscal policy can play a big role, but setting the fiscal policy right is at the front of this kind of debate in a way. So the objective of our paper are threefold. So what is the role of finance in carbon pricing? And when I say finance here, I mean the stochastic discount factor, because going back to the Lucas work, we know that the stochastic discount factor is the asset price. So understanding what would be the correct stochastic discount factor when we're thinking about the fiscal policy on climate is really, really important. And that's where the finance here is represented. Which modeling element under uncertainty are key in terms of trying to match the theory to the data. So this is where we're trying to bridge the macro theory to basically all the empirical data, and that's the macro finance usual divide, and I'll speak about this a little bit more in depth. And finally, then how implementing such an environmental policy, given that we identified the correct modeling approach and the correct stochastic discount factor, will itself impact all the macro aggregates and the financial prices. So it's the reverse question in a way. So what we do specifically is we contribute both empirically and theoretically. Empirically, we will be using statistical methods in the name of the simulated method of moments and a Bayesian estimation, which we take to a nonlinear solver and use data to try to discriminate between the main types of stochastic discount factor modelization that we can have and that the literature has been speaking about. And theoretically, we're going to show that habits formation is one of the ways that we will propose, and we show that it's the key one. What's the implication of having habits formation within our framework when we think about carbon pricing, and how does it impact the macro financial aggregates? And since I know like the audience can be all around the world, like probably for you guys in the US, it's the morning, so you're probably still fresh, but here in Europe and especially in some places, also maybe in Asia, it's very late in the night. I wanted to summarize the whole findings in one slide, so that way at least the main message is already said here, and then the rest will be more trying to elaborate more on it. So the main message of the paper is that the discount rate, at least in the current set of literature and papers that we have, lack a lot of empirical grounding and therefore fails to replicate the macro and financial prices. This is the usual macro finance divide. And that without realistic discounting and without realistic stochastic discount factor, and in this case, I call it a stochastic discount factor that incorporates habits formation at least, we will always systematically underestimate what is the optimal carbon price in the economy. And that one of the features that we find that is quite interesting is that this carbon price, once we features habits formation within the stochastic discount factor, comes up to be strongly procyclical, meaning that during recessions, we want to have the carbon price really, really low, but during booms, we want to have it really, really high, substantially more than the responses of GDP, for instance. And this is what we call strongly procyclical in this specific case. In a nutshell, some of the macro literature that we talk about, or at least the climate and macro literature that we'll be talking about, here I'm clearly not making any justice, and a lot of people have to forgive me here, but I just wanted to keep the slide a little bit more tractable and readable. But most of the papers are, or at least most of the literature is on the paper itself. And if I forget anything, please reach out to me. I'm really happy to look at that. But we're speaking to different type of literatures in terms of climate macro, and that spans from the early work of William Nordhaus to the latest work of Follini and al. We also speak to a lot of the work on the social cost of carbon and the climate risk uncertainty. And I think the uncertainty element is going to be clearly important. As I say, the climate macro would allow us to have the correct climate sort of modeling that we want to be following. The uncertainty element will be very important as a source of exogenous variation since we're taking the model to the data. And I think there've been a lot of work that's shown that uncertainty has substantial impact on carbon pricing. But finally, and most importantly, is the literature on climate macrofinance that, while limited, is still very important, that usually either uses power utility in terms of the utility function, and that's a lot of the work that follows Golosov and all, or recursive utility as it's been used in Kai and Lundzeg. And we contribute to that by taking this sort of frameworks, adding also an extra element of habits formation that is widely used in finance by John Cochrane and others, and essentially evaluate this empirically speaking. And I think maybe this is a good point if there is any question of clarification, if I wasn't very clear or anything like that.
No, I think you're doing great. Thanks.
All right, perfect. Then in which case, let me give you in a nutshell what would the framework would be, and then I will go in each one of these elements a little bit more in depth to tell you a little bit about what we do in each one of these. So our households, at least in the baseline model, will be a representative households, which we expand to some heterogeneity, so we'll have some heterogeneous households. But our representative households will have a utility function that both features the elements of recursive utility taken a la Epstein Sein and habits formation as Campbell-Cochrane. So where theta is this intertemporal elasticity of substitution and ZT here represents this stock of habits formation or habits, lifetime habits. These households will provide different elements such as like wages. So they work in firms, in some aggregate firms, and basically get wages for that. They also hold shares of the assets that would basically be used by the firms in order for them to produce, and also can save on some bonds. And I will go more in depth in all of this. But the main idea behind is that these households interact with firms. We have two sectors. We will have what we call a final firm, and we will have some R&D firms where these R&D firms produce some human capital, which then is used by the final firms in their productivity of labor. Both type of firms will be subject to an environmental externality, meaning that as the final firm and the R&D firms are producing units or productions, they're emitting CO2 emissions ET. These ET, CO2 emissions, the flow of emissions, it accumulates in cumulative emissions XT, and therefore it gets us some damages. And those are the DXT, those are the damages that both firms will be subject to as we have the externality. Now, in a world where we have the externality and the firms don't internalize as this externality, there is no action that can be done. Therefore, we have this market failure that the government will step in to try to fix. And therefore, we have the public authority that will step in and put in place a carbon tax that we call TET. And this carbon tax, for us to be able to retrieve the first best optimal policy, will be solving a social planner problem first, and then allocating this tax or setting this tax TET as equal to the social cost of carbon, which will be the shadow price of emissions. That's solution of the social planner, and uses this revenue of carbon taxes as transfers back to the households. So in a nutshell, this is the framework in itself. Now I'm just going to go a little bit deep on each one of these aspects. So the environmental externality and the climate dynamics, we follow Matthews and all science paper such that we get like a reduced form. Since we take the model to the data and we'll be using a nonlinear solver, we're trying to make it, at least on the baseline, a model that is more tractable and easily replicable. So we're using Matthews and all, where the cumulative emissions or the stock of cumulative emissions xt plus 1, so the future cumulative emissions, are today's cumulative emissions xt with some decay rate, and I'll speak about that, plus the flow of emissions, the flow of CO2 emissions, ET. We're doing, so all our analysis will be based on the US. So since we have data on the US at slightly a higher frequency, we're using this analysis to basically think about an economy of the US. So ET will be the representative American firm that will be emitting CO2 emissions, and E star will be the rest of the world. The iota X represents just a scaling parameter that basically converts CO2 to monoxide, so CO. Now, the delta X, this decay rate, as argued by Matthews and all, needs to be 0. We take it slightly different than 0, but very, very close, only for stationarity purposes, since we're taking the model to the data and requiring stationary processes. So we're taking it non-zero to not basically end up with a non-stationary process. However, our results remain very robust, and it's maybe a good place to say that, to basically delta extremely close to 0, and also to a climate dynamics that are a little bit more involved with different boxes and layers, such as the one that is presented in Foligny, and all the results remain quite robust to those specifications as well. Our climate damages are, in this specific case, related directly to the cumulative emissions. It is standard in the DICE literature to have temperature as an intermediate variable that essentially converts cumulative emissions. So rising cumulative emissions impacts aggregate temperature. Here again, just to keep it tractable, we relate it directly through cumulative emissions, and therefore the zeta will be calibrated such that we're basically matching it to the DICE type frameworks. So that's on the production side, that's equation 2, but also we allow ourselves to have a disutility from cumulative emissions. So as cumulative emissions are high, we get a disutility from that. Now, the purpose of having it in our specific framework is just to give us a little bit a degree of freedom in terms of matching some some price of CO2 emission that we match it to the Biden administration at the time where we basically did the paper. However, it's without loss of generality, and the results remain really, really robust to the eta, which is the disutility weight, equal to 0, meaning no disutility of climate, and that's the results remain pretty much the same. Probably also worth saying that we're not going to be speaking about the level of the carbon price. That's not really the aim of the paper. It's not to say whether the carbon price is 300, 400, 500, or 600. It's rather how does it differentiate between the different type of specifications. So the idea that we want to convey is if we think that the carbon price is X, by how much the X go up or down, and how does it variate over the business cycle given the different specifications. Why is that the case? In our case, that we don't really put too much weight on the exact price. It's because there are the 3 other elements that we don't necessarily want to go and explore, and they have been already spoken about by the literature quite substantially, and the debate is out there. So there is no reason to really put a really hard number in terms of the social cost itself, but rather the impacts of different specifications on what it would be. Emissions will be just a byproduct of production. So CO2 emissions ET are a fraction of total GDP, YT, where mu T is abatement. So as the regulator puts a carbon price in place, firms will have to engage on abatement. The gamma T represent the rate at which emissions decouple from GDP. So even when there is no regulation in place, we do observe emission going down in the US economy, meaning that decoupling rate is essentially negative, such that there is more energy efficiency. This is usually something we can think about as a positive externality of R&D. As we're learning more and we're becoming more efficient at producing, CO2 emissions are going down. That does not mean that we should not engage in any abatement, because the decoupling rate is still very low, but it does exist. So we're allowing for that by having a gamma T that is time varying and will be impacted by H, which is the human capital stock. So as the human capital stock is endogenous in our setting via the R&D, as H go up, the gamma T goes down, meaning the decoupling rate goes down, although there is positive growth in the economy. And the iota E is just the scaling parameter, which means that what is the value of it today at the start of the simulation, essentially. Our economy, as I already said, is composed of 2 sectors. There will be an aggregate sector and there will be an R&D sector. The aggregate is YT, the R&D will be called IHT, referring to investment in human capital. So the representative firm will use a Cobb-Douglas function, quite standard, where we're using both capital KYT and using some labor augmenting technology, which is the NYT. Those are the labor hours work. HT is the endogenous human capital that in this case will be produced, or at least via the R&D firms. A in this specific case is just the level of productivity, which we allow it to be subject to exogenous shocks in the name of epsilon AT, which follows an AR1 shock. Now, the damages, as you can see, are in the production function, and they impact it through a convex function of the cumulative emissions. The human capital accumulation is rather standard and following Kung and Schmidt, where the stock of accumulated human capital tomorrow is the stock of today, plus whatever investment we make in human capital. This investment in human capital is this R&D sector that we have that also uses a Cobb-Douglas function to produces using a Cobb-Douglas function where we use both capital and some labor augmenting technology on hours worked in R&D, those are the NHT. Same thing, it's subject to climate damages, and also we allow its productivity to be subject to exogenous variations following an IR1 shock epsilon 80. Our physical capital follows the standard law of motion where the physical capital tomorrow is all the non-depreciated capital today, plus a convex function that would capture the adjustment costs that we would have in terms of capital investment. And this is following Ehrman 1998, and where the aggregate stock of capital is the capital used in the final firm production sector, plus the one used in the R&D sector. And now I go to the probably central part of the paper, which is the household side and the utility side, because this is what's going to shape the stochastic discount factor. So the utility function in our specific case, we allow it to capture all the elements, which would be both the habits formation, also the case of CRRA if we would like to have that, as well as the recursive utility. So we're casting the two main elements that has been discussed in the macrofinance literature. So if I go back to that for a second, and going from the Lucas model where we only have a CRRA function, there's been a lot of work since then to try to bridge between macro and finance, because the usual dichotomy is we can't match both the aggregate macro variables and also the financial prices. And a lot of the work that has been initiated, whether it's by Epstein and Zine and Weiland with their recursive utility function, trying to de-associate the intertemporal substitution and risk aversion, or by Campbell and Cochrane introducing the habits formation, or even different other work that by Ehrman doing production asset pricing, or going through different heterogeneity within the household. All those kind of macrofinance frameworks try to address this sort of like dichotomy between macro and finance, or at least not being able to match all the elements at once. And in this specific case, we focus on, at least on the baseline, on two main elements, which would be the recursive utility and the habits formation. Now, the recursive utility is shown with the presence now of theta, the intertemporal of substitution, and the habits formation, which would be following a stock of habits, which we call here Z. We refer to as ZT, where the stock of habits tomorrow is just a weighted average between the stock of habits today and consumption. Now, in our framework, we also have growth, endogenous growth. So we will have this element of long-run risk with respect to climate, and we will expand the model to also include heterogeneity within the household, having two types of households, some hand-to-mouth and some savers in our specific framework. But in the main framework, this would be the one, and I will present later on the results, some of those robustness that we make when we take the model slightly more to different ways that has the literature has tried to think about the macrofinance divide. Yes, Rick.
Good. I just wondered whether you thought of having those habits, having green habits and brown habits, that you may be rather attached to your brown habits, forcing you to move across the green stuff rather less flexibly than you would have done otherwise. But you have your habits in aggregate consumption, is that correct?
So the habits here are on aggregate consumption. Indeed, I think might be a good idea. In our framework, we don't have like two different sectors. I think to be able to do what you have in mind, would it would require maybe having two sectors, right? Some brown and green sector.
Or at least two consumption goods. But say you have brown consumption and green consumption. But I think then you may have your habits in brown, preventing you to switch to green more quickly than you would have done otherwise. But anyway,
it's a good idea. I should think about it. Thanks. That's a great idea. We haven't thought of that. Thanks. But indeed, so in our case, we have like an aggregate consumption good, which is one consumption good, and over this one, the household will be making their choice over how much to consume, how much to save in some riskless assets and bonds, and some shares to detain on the firms, the claim on the firms, for which they receive wages on the hours worked, they receive some dividends and the prices of these shares, as well as the returns on the bonds. And they do pay some lump sum taxes. I mean, they could either be taxes or transfers, depending on their sign. The government in this specific case will be just a passive government where essentially there will be no debt in our economy, and the government spending will be a specific portion of GDP. So say GT is 20% of GDP, and therefore the lump sum taxes will be defined as such, using also these taxes that we get from CO2 emissions. This is a simple definition of our competitive equilibrium, but I already hinted at that. Our competitive equilibrium in this setup is that each one of the agents will solve their maximization problem. So the households solve their maximization problem, and the firms solve their maximization problem. And then the government will intervene to fix the climate externality inefficiency by setting the tax on emissions T of ET, this tax, such as it's equal to the social cost of carbon. So at first, we solve the social planner. We identify what is the shadow value of CO2 emissions, which will be the social cost of carbon. And then in the decentralized equilibrium, the government just sets the tax equal to the social cost of carbon, such that we retrieve the first best equilibrium. And as I said, the main component of what we do here is the stochastic discount factor, and this is how it looks like in our specific setting when we're casting different elements from the macrofinance. So the stochastic discount factor has, here I only highlight 3, but in fact there are 4. So the gamma T, which is the long run risk, so the long run growth factors that, so that's one of the other 4 elements. But the three important ones will be the early resolution of uncertainty, and this is the recursive part that comes from the recursive utility. I have an element that comes from the climate disutility, and as I said, the results remain robust to that. This is just a degree of freedom to allow us to basically match a specific carbon price that we have in mind. And finally, the one that comes from the habits formation. So this is how the stochastic discount factor looks like in our setting. So it's an object that is somehow tractable and also allow us to move between all specifications by just setting theta, the elasticity of substitution, to 1 minus sigma. We can collapse back to the case of CRRA as long as ZT, the habits formation, is set to 0. So we can basically move across all the blocks quite easily by framing it a little bit more in the way that we do. And as such, the carbon price, and again, I think the notation here is not really the most important. I think it's what's under the notation. It's more like the wording of it. So the social cost of carbon will be a function, as I said in the beginning, of the stochastic discount factor, some long run growth, a disutility from damages, and the production damages, plus some continuation value that is impacted by the climate dynamics, the delta being the decay rate in this specific case. While I'm not going to basically look, or while we don't look at the production damages, the disutility damages, and those continuation value or climate dynamics in a very much more in-depth as the other papers do, we take the latest from their work to basically motivate our research and really just focus on the stochastic discount factor in here. And given the time, so this was just more on the slides because I think later they can be made available. So I left some sort of the calibration. So now, once we have set up the model and explained the 2 main components, which will be the stochastic discount factor and how it will interact with the social cost of carbon, let me take you to the results, and let me take you to the part where the action really happens. So what we will be doing here is we will take this framework to the data. And the first way we do that is we use simulated method of moment. This goes back to because Yvon is a big fan of that, and he comes from the finance literature, and usually we want to make sure that the model is robust without having too much exogenous variations. So we're only going to use one shock in this specific case, which is the TFP shock. And using just the TFP shock, we're going to try to match different moments, macro moments, finance moments, and environmental moments, to see which one of the different frameworks, is it the Epstein-Zine, is it the habits, is it CRRA, which one of them is able to replicate the data. And that's the first exercise we conduct here. So whenever we don't necessarily match a moment, and therefore we do here use some set of parameters, those parameters will be calibrated to match just some specific aggregates. For instance, productivity level here is set such we match the GDP level in the US, so on and so forth. But this is the SMM strategy, so quite standard, using from the work of Hansen, the early work of Hansen, and then we take the aggregate estimator to just get our values of the parameters given the moment that we want to match. These are the parameters that we will be estimating such that we're matching the set of the targeted moments. And let me just focus on the set of targeted moments, which is what we have in this table. So here we have as many moments as parameters. So we're not under-identifying or over-identifying. And the moments that we target, as I mentioned, there are many that are macro aggregates, some that are finance prices, and we also look at what happens in terms of like some non-targeted moments, such as emission growth, which are the climate side. These are just the symbols to relate them to the paper to make it easier for the reader. And the third column we have are the data. So the first element, so for instance, output growth mean, this is set at 0.65. This essentially is the mean that we see observed in the data for the US between 1976 and 2023. And these are the confidence interval depending on the time span that one can take. And then what we show here is two cases, although we have actually all the cases, which means we have the case of Epstein-Zine, only habits, only CRRA, or Epstein-Zine with habits. But just to ease for the reader and for you today, I'm just presenting you two cases, which is the Epstein-Zine with habits versus CRRA, which was the widely used in the climate literature. And what we see is that the Epstein-Zine with habits, when we're matching the data, when we're matching the output growth mean, the output growth standard deviation, the equity premium mean, standard deviation, and so on, we're able to do a very good job. So the model that features both Epstein-Zine with habits does a very good job to match the model's moments to the data, while we see that the CRRA model fails to do that. And whenever you see a star, those means that those are the moments that we target. So for CRRA, for instance, we cannot target as many moments because we don't have as many free parameters. It's a model that is more reduced, while in Epstein-Zine we have intertemporal elasticity of substitutions and so on. So the CRRA is clearly not able to replicate all the moments, and this is quite known in the literature. We know that CRRA alone is not able to capture all the moments between macro and finance, while the Epstein-Zine with habits is able to do that. Now, I'm not presenting the other two, which is just habits or just Epstein-Zine, but both of them are also not able to do as good as a job as Epstein-Zine with habits. And with respect to non-targeted moments, we also do quite a good job with our model to basically be able to get them very close to the confidence intervals. I mean, potentially just the Tobin Q, but it's not far-fetched from the confidence intervals that we have. So this is the first kind of like statistical test that we run to already show that the CRRA is clearly not the right approach, and it will have substantial implications, while the Epstein-Zine with habits seems to really do a good job here. So one can even think about it outside of even the climate space. This is an interesting result in macrofinance in general. And now what we do, because the estimation, or at least the matching moment that we do it on the laissez-faire economy, given the US does not have any substantial carbon pricing. And now we run a counterfactual, which is what happens when we put a carbon price, and what happens if the model that we choose is an Epstein-Zine with habits versus a model that is just a CRRA standard utility function. And what we're able to show here is that the implications of carbon pricing, which is the third or the fourth column over here in green, seems to have implications that are very different at first glance between the Epstein-Zine with habits and CRRA. If anything, in fact, it goes in the opposite direction. To speak about it more simply, once we put a carbon price in the economy, we can clearly see that the equity premium goes down by 26 basis points, and as well as the standard deviation, meaning that the carbon price is able to eliminate some uncertainty from the economy. As such, people don't have to engage in as much precautionary savings because the carbon price is acting as a sort of like a hedge and a safety net. And we can see that the risk-free rate is going up as a consequence of that. And this is what we could think about it also and rationalize that from an economic perspective. And that's something we're able to get quite nicely with the Epstein-Zine with habits formulation. While when we look at it in terms of the CRRA, we get pretty much the opposite to that, where essentially what we see is that the risk premium is actually standard deviation is going up, meaning there is a little bit more risk in the economy. And this already difference between both is quite striking and tells us that the approach that we've been thinking about in CRA, at least probably, is not necessarily as good, especially when we think about the implementation of the carbon pricing. And here we do run it for, and I mean, given the time span today, I'm not going to have much time to go through this, but the main idea of this table, and that's why I left it, although I'm not going to go through it more thoroughly, is to show that the results of the baseline, so the first line, remains really robust to whether we put some sort of tax schemes that are fixed. So we basically say the carbon price does not covariate. We just set it to its steady state. If we change the income dividend taxes where we allow the transfers to be adjusted, or if we basically allow the government spending to be adjusted, whether we set the exogenous growth to a fixed growth rate, whether we have some neutral preferences to this utility, or even when we have heterogeneity in the household side. The results remain really robust to our baseline model. Second, then, as SMM only relies on one shock, we already showed that just with one source of exogenous variation, we're able actually to find some very interesting result that tells us that Epstein design with habits is potentially the right tool. We still take it with more exogenous variation, where now we include different data sets, so macro data, climate data, and financial data. So the financial data in the name of the risk-free rate and the equity premium. We have some output and consumption growth, and we have the emission growth rates. And we're going to use it with a nonlinear solver. So we go to up to the third order, and the third order will be very important here. And it's not because we want to be fancy and we can do that. It's actually because it's really important. And we use some Monte Carlo chains to basically be able to draw and sample on the draws from the prior distributions. And the main idea here of the SMM is to try to really convince you that the Epstein design with habits is actually the best type of model. So what we do is we start with some sort of prior distribution here that is equivalent between all the four specifications: Epstein design with habit, Epstein design, habits, and CRRA. And then we look at what happens after we basically do our whole estimation. Which model is more likely to replicate the data? And we find that here, the Epstein design with habits is the most likely to replicate the data. We can see it through the log marginal density. It's the lowest one, while the habits is actually the closest to it, and it's actually not too far from it, which means if anything, if one wants to give up in somewhere, one gives up a little bit on the Epstein design, but we need really to keep the habit. So habit seems to be really where the action is happening. And we can see it clearly on the posterior probabilities, which is the Epstein design with habits is the most likely, followed by the habits model. And this is a statistical way that allows us to discriminate between these different type of models that we've been looking at in this paper that have implications that are quite important in terms of carbon pricing, but also more generally in terms of macrofinance. We go and take it a little bit even further and show that actually from a finance perspective, we're able to show that the Epstein design, or at least the Epstein design and the habits, are the ones that are really important and allow us to be within the confidence band when we're looking at asset predictability. So as you can see on the graph on the right, the only two specific models that are between the confidence bands when we're looking at the equity premium are the Epstein design with habits and the habits model. So this is a further test to testify to the importance of these two, and at least to show that it's basically falls within the confidence band, even when we're looking at predictability of asset returns. And maybe the graph of the paper, and I'll finish on this. Here, what I'm showing is this is stationary, so there is no sort of like the model is stationarized, so I'm not plotting it with the growth rate. Maybe it's smarter to do that, but we're doing it this way, so just we're able to see those variations more clearly. So we have the four models: the CRRA, the habits, the Epstein design, and the Epstein design plus habits. And what we're showing is that in yellow, the CRRA model give us a very low price with very, very low variation. And here, please don't focus on the dollar value. Again, that's really not the objective of the paper. It's more the variation, the differences between the different prices, the different models. The one that generates, and as the one that has been taken by the data to be the most likely to replicate the data, is the Epstein design with habits, which is the blue one. So we find it to be both the highest in terms of level and the most pro-cyclical fiscal policy among all the different specifications. So having the right type of utility function and thus the stochastic discount factor have substantial implications in terms of the fiscal policy that we want to conduct, especially when we're thinking about business cycle variations and the inclusion of uncertainty within that specific topic. And this is about the third order, why the third order is really important, especially when we're going to these ideas and when we're thinking about the estimations, and one needs to really go to that, because the stochastic discount factor from which the whole implications comes through only starts to variate at the third order, where in the first and second order, as we can see on the right, it does not pretty much move. Okay, the movements are really small, and the whole movement comes from the third order. And as such, we really argue that going to the third order is very, very important. So that's one of the elements here as well, that probably the contribution that can be more like set at the technical level. And here I leave you with the main takeaways again, which basically are the exact same ones that I spoken about in the beginning. And I don't know if I did a good time managing the time, but I hope I did. Again, having a really good grounding of what should the discount rate be will be extremely important, because not including at least habits formation would drastically underestimate the carbon price in the economy. And we find it to be strongly procyclical, especially when we include this habits formation and Epstein sign as well. And that will have like clearly a big importance in terms of policy making as basically we go ahead, especially if we want to achieve the net zero by 2050. And with that, I'm very open to get questions and answer it as it goes. Thank you.